meter away. What is the electric potential here? Well, I got 9 nanocoulombs, so my electric potential at this point, KQ over R, so that's roughly 9 times 10 to the 9th, times Q of 9 times, what's a nanocoulomb?
Is that 10 to the negative 8?
Not 8,
6?
by the way.
Oh,
By the
10?
way.
Oh, 4?
No,
I mean,
when a larger magnitude. It's usually multiples of 3, so
oh,
not 8.
3. Okay. So 9?
Yeah, negative 9. And that's why I chose nanocoulombs, so that it would cancel out with that. Over R of 1. And so we end up with an electric potential of 81 volts. So 81 volts. If I go out here and I'm at 2 meters, so an extra meter, so 2 total. What is my electric potential here? Okay, 40.5. If we go out, let's say another, let's go out 3 meters. So if we go out another meter, what's my electric potential here?
27 volts.
If I put a charge, say I take a proton, I stick a proton right here. Based on what we know, which way is that proton going to move? Aaron, was that it looked like you started and then you changed your mind?
No, I was like, focused.
Which way will the proton be forced?
It's a positive 9 volts, right?
Yes, that is a positive number.
It's gonna be forced to the right,
Okay. Why?
because they're both positive, they're gonna repel.
All right, go with force explanation. So the proton is going to be moving in that direction. If I put an electron here, which way would the electron go?
To the left.
All right. So I made it negative 9 nanocoulombs. Oh, I did leave one thing out. That whole plus a constant. When we're dealing with a constant, this gives us the flexibility, because what really matters is the change in electric potential. So the constant allows us basically to establish 0 wherever we want. All of these right here make an assumption, and let's just go ahead and state it, that the electric potential equals 0 at R is equal to infinity. We're establishing our constant as 0. All right, so I put my electron right here. We know it's going to go to the left. That's right, I was down here. So I have negative 9 nanocoulombs. If I'm 1 meter away, assuming that V equals 0 at R equals infinity. What's my electric potential here?
So is it gonna be negative anymore?
Yep. If I go another meter out,
And then negative 40.5?
give me the units.
Oh, is that volts?
It is.
Volts.
Ooh, and I left it off there. Somebody should have called me on that. So if I put an electron here, which way will the electron go?
Right.
If I put a proton here,
To the left.
so what is the pattern here? The proton always moves what? In terms of electric potential. It's doing the same thing in both cases. So here it goes from 40.5 to 27. There it's going from negative 40.5 to negative 81.
It's increasing?
Say it again?
It's increasing
What's increasing?
the volts, the electric potential?
40.5 to 27 is increasing?
No.
Decreasing.
What about negative 40.5 to negative 81?
It's
It's
decreasing.
still decreasing.
Yes. Positive charges will always be forced towards the lower potential. The electrons, the other way. And part of this, if you think about it from a logical point of view, or logical/historical, when they were first coming up with the conventions, actually, who's the person who came up with the convention? Why are electrons negative and protons positive as opposed to the other way around? Who's to blame? It's an American. It's the kite flyer.
Did you?
Yep.
Franklin?
Benjamin Franklin is the one who established this. He was a well-known scientist, basically the first major American scientist.
Did you say that positive charges will always be forced to lower potential?
The positive charges are always forced to a lower potential. Lower electric potential, if we want to get more precise. Negative charge is the opposite. So for a negative source here, so this negative charge, the farther away you get, the higher the electric potential. Protons flow towards the lower potential, so protons, positive charges will be flowing towards it. Negative charges flow to a higher potential, so an electron would flow away from a negative charge. Positive charges, the electric potential decreases the farther out you get. Protons will flow in that direction, electrons flow the other way. Oh, back to the thought I started earlier. When Franklin was first devising this, he thought in terms of water flow. It's the reason we call the electric current. And he pictured this fluid that was flowing. And if you think about water, water flows downhill. And so he pictured this charge, whatever the substance is that's flowing, flows downhill. So we have, so thinking in terms of positive charges sort of defining everything, this is downhill. Protons flow downhill. It wasn't until 100 years later that they realized that there were these negative charges flowing in the opposite direction from what the standard said. But at that point, it was too late. They were not going to change. All right, questions are here before I actually talk about what voltage is. That up. So I have a configuration. Assume I've got charges set up so that my potential here is 3 volts, my potential here is 4 volts, my potential here is 5 volts. Whatever my charge configuration needs to be to make that happen. Which is one of the advantages of talking about this, is I really don't need to know what the charges are, I just need to know where my potentials are. I have a particle that starts here at the 3 volts, and then goes to the 4 volts. What is my change in electric potential?
Positive 1.
Yeah, positive 1 volt. I start at the 3 and I go directly to the 4 volts. What's my change in electric potential? I saw a finger back there. Yes, it is the same. Path doesn't matter. If I start here and go to the 5 volts, what's my, using better terminology or more common terminology, electric potential difference? Let me write that up, electric potential difference.
2 volts?
Yep. And then I start at the 5 here, and I go to the 4. What is my electric potential difference? Yes. It's always final minus initial, negative 1 volt. I'm sure people have written this stuff down before I drop the connection with other things I've mentioned. This electric potential difference, that is voltage. If I have a 12-volt battery, what the claim is that the potential difference from the bottom to the top is 12 volts, or negative 12 volts, depending on which way you're going. So imagine the classic AA or AAA battery. That's the positive side, that's the negative side. All that I know is that the potential difference between it, if I'm going from negative to positive, the potential difference is 12 volts. If I'm going that direction, it's negative 12 volts. Which is why it matters if you're putting a battery into a circuit, there's a special way to put it in there, because one way is trying to force current going to flow one direction. If you flip the battery around, it's trying to make current flow the other direction, which matters in some devices. Now, the textbook, not every textbook, and I cannot remember specifically about yours. Some textbooks are very picky about it, and some textbooks are, let's just relax, let's just use the same symbol for potential difference and potential. Here's the reasoning. I was thinking that the OpenStax book is more of the relaxed variety. Because the electric potential is that formula plus a constant. Then I can, basically it allows me to establish 0 wherever I want. So electric potential difference, or voltage, is equal to the final potential minus the initial potential. If I can make 0 anywhere I want, why not just make that 0? And therefore this, I have only one potential now, and so the thinking is, well, that is just equal to my final potential, or why don't I just call it my potential? This is the logic here for why some textbooks will just put a V instead of a delta V. Just please be aware that if the textbook or some source is using a V instead of a delta V, they might be talking about voltage and not the electric potential. Or they might be talking about electric potential and not voltage. I will try to stick with the delta V. Just so that you, at least in your notes, you can differentiate, oh, he's clearly talking about voltage here, he's clearly talking about potential here. And you might have to translate for the textbook. So I back in my battery, 12-volt battery. I sort of contradicted myself. I said it was a classic AA or AAA, and then I made it 12 volts, which isn't the way it works. But let's just assume it's a 12-volt battery. If my potential here is 0, what is my potential here? 0 volts. What's my potential here?
12.
If my potential here is 100 volts, what's my potential here?
112.
If my potential here is -5, what's my potential here?
7.
Trying to emphasize the fact that voltage is just the difference between those two spots.
there a difference between negative 12 volts and 12 volts?
The difference is 24. It matters which way you're going. The direction that, because if I have a power source, positive and negative sides, and a circuit here, this is trying to force the current this way. That's the symbol for current, is capital I. So it tries to force the current this way. We're gonna get into what is known as Kirchhoff's rules. He has two different rules for doing circuit analysis, which is test 1B. And it does matter which way you're going across the battery. So that, the realistic difference shows up in chapter 20. Other questions? Right. All right, so that's the basics right there. Recognize we've only talked about one physics formula. That is the force between two charges. All the rest is just math and definitions. In 151, there are typically 3 physics equations. All the rest is just math and definitions. 3 physics equations from 151 are F equals ma. The gravitational force being big G m1 m2 over r squared. And for ideal springs, F equals negative k delta x squared. No, sorry, negative k delta x. Those are the 3 from 151. We have this formula here. There's going to only be really one other physics formula in this course, and all the rest is just math and definitions. The second formula we will do comes with magnetism. We're not there yet. I was just about to do something and then, oh, that's right. All right, questions? I'm about to drop back just a little bit. Talk a little bit about the electric field. All right. I have a positive charge, some positive charge here. Assume Q is a positive number. What can you tell me about the electric field?
It's pointing away.
Okay, so an electric field pointing away. And the formula?
KQ1 over R squared.
And you said Q1?
Y'all did say Q1, because isn't the electric force on one the Q?
Yeah, well, I mean, this is the electric force created by that charge. And since I labeled the charge just as Q instead of Q1, that just Q.
That's it, matches.
All right, all right, all right. If I am here, so what I'm gonna do is I'm gonna create a fake object. Imagine I've got this charge in the middle of a sphere. So I've now surrounded this by a virtual sphere. This virtual virtual, so just an imaginary sphere, is known as a Gaussian surface. A Gaussian surface is any sort of three-dimensional imaginary object that we do to surround a certain segment of space. We just happen to have a charge inside this one. And I'm putting the charge smack dab in the middle. the area vector, this is the area vector. The area vector is obviously a vector which points perpendicular to surface. And if closed surface, further now it's probably work here. If closed surface, area vector points outwards. If open surface, area vector points one of two ways. So for example, if I think about this as an open surface right here, and open and closed surface is a matter of, can I get from one side to the other without going through the object itself? So this right here is an open surface, because if you just imagine this is a plane, I can get from here to the other side just by going around it. Whereas this would be a closed surface because I can't get from this side to the inside without going through the surface itself. If I took the top off, it suddenly becomes an open surface. But with the top on, it's a closed surface. We will imagine that the hole right there leading into the tube does not count. The magnitude of the area vector, so that tells us this is about the direction. The magnitude of the area vector is the area of the surface. So this board right here